We talked about constant volume calorimetry using the bomb calorimeter. And then we talked about some constant pressure calculations. And so now we're going to talk about constant pressure calorimetry. So this can be used to measure the heat of reaction, which is the change in enthalpy for an aqueous reaction. And we could do this in what we call a coffee cup calorimeter. And as the name suggests, it's made out of styrofoam coffee cups. So 2 styrofoam coffee cups. This is showing a cork lid. We'll be using a cardboard lid when we do this in lab. We've got a thermometer here, and the reaction is going to occur inside the coffee cups. We use 2 cups to get better insulation. Ideally, we would have no heat escaping from inside the calorimeter to outside. Because this is open to the atmosphere, we have constant pressure. We can measure the effects of the reaction on the solution. We can measure the change in temperature. So the heat absorbed or lost by the solution will equal the mass of the solution times the specific heat capacity of the solution times the change in temperature for the solution. That is directly related to Q for the reaction, which is what we're interested in. Q reaction and Q solution are the same number, but opposite in sign. So we can calculate Q solution, that thing. We can calculate this thing, and then we multiply by -1 to get that. Q reaction is the same as Q at constant pressure, which is the delta H for the reaction. That is usually given in joules or kilojoules per mole. And so we'll just divide by the moles of the substance that reacted. So here is an example calculation. The addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to this reaction. When 50 milliliters of 0.1 molar AgNO3 is combined with 50 milliliters of 0.1 molar HCl in a coffee cup calorimeter, the temperature changes from 23.40 degrees Celsius to 24.21 degrees Celsius. Calculate delta H for the reaction as written. Use 1 gram per milliliter as the density of the solution and a specific heat capacity of 4.18 joules per gram degrees Celsius. Okay, lots of words, lots of numbers. Well, let's highlight the numbers. It's a good place to start. There's several of them. And then highlight the question. We're trying to find heat of reaction. So what we're looking for, didn't mean to do that. What we're looking for is delta H reaction over here. That's going to give us the amount of energy change for 1 mole of this and 1 mole of that. Okay? We cannot calculate directly Q reaction, but we can calculate Q solution. We know that Q reaction is equal to Q solution times -1. And Q solution is equal to the mass of the solution times the specific heat capacity of the solution times the change in temperature for the solution. So if they actually want us to solve this, they should have given us enough information to find all those things. So let's look for those things. Did they give us a mass of the solution? No, they didn't. We can find it though, but they didn't give it to us. So we're mixing 50 milliliters of one solution with 50 milliliters of another solution. So what's the total volume? $100 milliliters. we can use density to convert volume to mass, or mass to volume. And again, we're going to use density as a conversion factor, bless you. So I want mass, I have milliliters. I'm going to multiply by grams and divide by milliliters so the units work out. So much less thinking this way. They gave me the density, 1.00. That's the number of grams per 1 milliliter. 1.00 grams per 1 milliliter. And so in this instance, it's the same. So there's the mass of the solution. So this is going to equal 100.0 grams. And then we need the specific heat capacity of the solution, which they gave us right here. And then we need the change in temperature for the solution. Well, they told us, whoops, that's not what I meant to write. They told us that the initial temperature was 23, right? It went from 23.40 degrees Celsius, and it ended up at, what happened?
It's the light.
24.21 degrees Celsius. I lost some of my highlight there. So, how do we calculate delta T? It's the final minus the initial, right? So I'm going to take the final temperature, 24.21 minus 23.40. The change in temperature is 0.81 degrees Celsius. So that's the change in temperature for the solution. 0.81 degrees Celsius. And if I check my units, grams cancel, degrees Celsius cancels, and I end up with Q in joules. Sounds pretty good. So 100 times 4.18 times 0.81 equals. And if we're thinking about sig figs here, this guy only has 2, so that would be a last sig fig. So that's Q solution. How do we find Q for the reaction? It's -1 times Q for the solution. So it's just negative 338.58 joules. The solution got warmer because it absorbed heat. The reaction lost heat, so Q for the reaction is negative. But this is the amount of heat when 50 milliliters of 0.1 molar silver nitrate and 50 milliliters of 0.1 molar HCl react. And to write delta H for this reaction, we need to find out, well, what would the amount of heat be if 1 mole of this reacted? So what we need to do is we need to find out, well, how many moles reacted here? Well, at 50 milliliters, so we could write that as 50.0 times 10 to the minus 3 liters, reacted with 0.100 moles per liter. The volume and concentration of each of these reactants is the same, so the number of moles of each is the same, and the mole ratio is 1:1. So there's no limiting reactant here, they just come out just right. So if I figure out what that value is, it's 0.005. that should have 3 sig figs. So this was the amount of energy. Oh, I stuck it in the wrong place. There we go. This is the amount of energy released when 0.005 moles react. So if I do the division here, I end up with negative 67716 joules per mole. And again, we should have 2 sig figs on that. A big number like that would probably be expressed in kilojoules. So we can convert to kilojoules by remembering what kilo means. Kilo means 10 to the 3. So 1 kilojoule is 1 times 10 to the 3rd joules. So this would be minus 68 kilojoules per mole. So up here, delta H then is minus 68 kilojoules. Any questions? We're going to skip this one because I don't think that really matters. How's that?